Hi. I do not know if anybody is watching this because Twitch does not seem to want to tell me. Um, but the plan today is to do some hardware stuff with actual hardware. And the first part, I thought that my life was too straightforward. There were not enough cables. And so what I need to do is repair this temperature monitor I made in the past so that it can be plugged back into things. And so to make my life as hard as possible, that's flipped. To make my life as hard as possible, I've decided to add a really heavy soldering iron and this one. Now we're the right way up. Add a really heavy soldering iron and a bunch of wires and heat so that I could sit here and burn myself maybe, or I don't know, knock the oscilloscope off the table. And so what this is, let me see what this ping is about first. Oh, Ed's here. Hi, Ed. So the stream today is going to be me trying to figure out how to drive some LEDs, and I'll get into that. But first, I thought I would just start by soldering this. This is less prepared than the previous ones, because I thought I didn't want to prepare. And so what this is it's a Adafruit Trinket clone. The clone was made by Hackaday. And then directly soldered to it is a USB serial adapter because I don't think things through very well. And then also soldered to it is a DHT11, which is a digital temperature sensor. And there are four neopixels on a strip. And so what is broken, if I poke it with a pencil, is the power for the neopixels. The line came off when I took it out of the testbed at work. And I use this as just a real approximate status indicator of temperature for my testbed. The testbed I have at work is a bunch of APU2 boards, and they sit on some shelves, and they're a mess, but they're very easy to get into and to play with and fiddle with. Oh, I didn't find a solder sucker. They're very easy to fiddle with, and so they sit on a shelf. But next to the shelf is the heating pipes for the building. And I was worried for a while that the APU boards were getting quite hot. And initially they were just stacked on top of each other. And when they're stacked on top of each other, they have metal shells and they're passively cooled. And while they're rubber feet, it was all a bit warm. And so I put this together one day because I was probably procrastinating from something really dull at work. And I needed temperature. And so this is a temperature sensor, which is the blue thing by the soldering station. And there's some LEDs. And so what this does is it checks the temperature every, 5 seconds or something. And then it sets the LEDs to one of three colors. If it is above a certain temperature, it sets the LEDs to red. If it is between that temperature and the low temperature, it makes them orange. And otherwise, it makes them blue. This is not a very scientific way to evaluate the temperature for your testbed. But it was a throwaway thing I did in like 20 minutes, as you can see, because the soldering has fallen apart. And it's worked fine for like 3 years. It's been no problem at all. I actually think I made this because I was having an argument with a colleague about the temperature in the room. But it's been helpful because at the university, they turn the heating off over the weekend, or if it is cold. And Aberdeen doesn't really get that cold, but sometimes it might get down to like -10, -15 overnight in the winter. And so it's interesting sometimes to come into work and see that the temperature has gone blue. And I think blue is like 18 degrees, so it's not even getting that cold in the room. And it's nice in the summer. If anyone ever complains that it's cold and I have too many fans on, I can be like, no, temperature red. And so it's a real nice vague indicator of my preference for how things should be. So I'm just going to tack this back on. It should take like 5 seconds. It won't, because that is how things work. And I don't have enough room at all to do any of this, because these are the things I do for you, my viewer. And so I'm just going to retin the exposed piece of wire so that there is some solder and some flux. And this is going to be really difficult to do. Please make fun of my soldering. I don't care. There we go. Wow, look at that. That's a giant blob of solder. And I am not sure I can do this and keep it on camera. So I'm not going to worry too much about it. As you might have learned from the last stream, some things I'm happy to do very well. Other things I don't care about, and I'm happy to just do whatever works. And so that is it tacked back on. You can tell because I can now pick it up with the wire. I don't imagine this will be durable for very long. I don't really care because it's moved once in 3 years. And if it has to move again and it has to be resoldered, maybe I can neaten it up. And so what I'll do is I'll plug it into my laptop and we'll see if it works. And if it doesn't work, we'll just go on to the next thing because I'm planning on spending a lot of time debugging today. And so I don't need to spend any time debugging the thing I didn't really want to do. So we connect it to the USB serial. It also logs on the USB serial the temperature, which might be nice. Who knows? And so you see the trinket comes to life, and I think it waits 10 seconds. Oh, and it turns on the LEDs. And so it's fixed. And the temperature in here today is orange. And if we... Well, I found the window, but now I have to find the right terminal. If we look in dmessage on my ThinkPad, we see an FTDI device. It'll be the first FTDI device. I have no idea what the baud rate is. Let's try the slow baud rate, which is the default in the Arduino environment. Hunter 2. Hunter 2. Yeah, okay. And so the Arduino, when you connect to it over serial, will do a reset, and this is how it does programming. And so this is printing out the temperature and the humidity. It's really difficult to tell which is the temperature and which is the humidity, but I think if I hold this and it doesn't die while I hold it, the temperature will go up. And this is the approved method of verifying your temperature sensor works. Just squeeze it for a while. If you want to go down in temperature, you need like a glass of water, maybe something ice. You can touch the sensor to the side of it and it will change temperature too. This is not changing temperature, so I have no idea what's going on. There we go. See, the numbers have swapped. And that is helpful because it tells us something. I have no idea. Yeah, so I think the second number is probably the temperature and the first one is maybe the humidity because the humidity changing makes sense. But anyway, there we go. There's a temperature sensor. And this is an example of a really simple status thing. I can only make it get hotter right now. I don't have ice. Well, I do have ice because I'm indoors like always. This is an example of just a really simple status thing, and it's it's an Arduino. It's probably like a $10 part normally. You can buy these. I mean, you can buy all of these pieces on eBay. They'll arrive in the next 1 to 800 years right now, but normally pretty quickly. And you could put something like this together. And if you just need like a visual indicator of what is going on, then this is actually a great way to do it, because I'm a bit distracted by RC. My hands were nowhere near the hot bit. It's fine. And if you burn yourself, you take the soldering iron away. Oh, I can turn the soldering iron off. Soldering done for the day. And I'm going to move it while it's hot because I don't really care. And I should also probably treat it better because it's not mine, but I'm not going to worry. But this is an example of a real simple way to get status that you can use. And if you just needed power, then just like an Arduino and some LEDs, you could plug in with a sensor. You could have status somewhere. Maybe you want to see the temperature in your garage. And if you want to do logging, actually going from here to logging can be on the scale really easy or really hard. Do I dare move the camera? If I swing the camera, what are we going to see? If I swing the camera around, we see my electronics box there, and in the focus. No, it doesn't want to focus. In the top right is ESP8266. These are sort of they're not end of life, but they're becoming less popular. ESP8266 is it was meant as like a Wi-Fi controller. You could add to like an Arduino and add Wi-Fi, but it turns out there was more processing power spare on the core than there normally is in an Arduino, and so they became their own environment. So that you can run Python on them quite happily. and they give you Wi-Fi. And so you could take what's set up here. I mean, but DHT11, NeoPixels, ships in the MicroPython environment. You can build a logger, and it could log to your network. 5-10 minutes, probably an hour to program the ESP, and then like 5 minutes to wire things up and make sure things work. And it's really straightforward. And so this is not great. I mean, I'm sure it used to be when the Arduino came around, there'd be all these engineers saying like, this is ridiculous. You're wasting like a $30 component making your cool project that makes you happy. And we could ignore those people now, and we can just make things that we want to make, and we can make them really straightforward. Equally, I don't know about DHT11 support in FreeBSD or NeoPixel support. So the particular temperature sensor and LEDs here might not be the most straightforward things to get going in FreeBSD. The LEDs we're going to use next will be easier to use if I get them working, and they'll be harder to use if I don't get them working. And the temperature sensors, there's loads of temperature sensors, and actually one-wire temperature sensors are probably a better thing to buy, and you get them in nice enclosures where, excuse me, I want to take this apart. You get them in nice packaging where they're waterproof, and so you can submerge them, and because they're waterproof, they're sort of weatherproof. And that was the plan for BSDCan this year, but BSDCan is a virtual event, and so I won't be doing that. But these are things you can add together, and you can just throw it together, and you could actually make like a nice little home monitoring system from just bits like this, once you know they exist. Okay, so I need a mini USB cable. Who would think at this point in 2020 that mini USB cables would be the cable I need the most? Okay, so we have a mini USB cable. And so the thing I'm going to try and do today is I have this little, I have this little LED strip. This LED strip is made by the worst named company in the world, Pimeroni. They make Raspberry Pi stuff. I had this tab. This one. OBS gets sad when I do this. Yeah. So this is the Pimeroni. It's called the Blinked. It is a little status LED. It uses, I need to look at the actual page to read it. It uses APA 102 RGB LEDs. The LEDs have an integrated driver. What this means is that the LEDs themselves are a small package, and so each of these white dots is a RGB LED. It comes in a 6-pin package, and the 6 pins, they take power, and I think power is 5 volts, but we're going to go find out. They take power, they take SPI data, and each LED will take power and data and then pass it on to the next LED. And they have their own drivers inside for the LEDs. And so normally, if you're talking about the amount of power available to you from a GPIO, it's actually very low. The amount of current you can sink might be like 18 milliamps less, and the consequences of drawing too much current from a pin on a single board computer, or normally the single board computer is dead. If you're lucky, a bank of GPIOs is dead. But normally you're throwing away like, I don't know, a $30 board, or if you use something cheaper. The LEDs with the driver, they mean that you can wire this up, and they get their power because you supply power separately to the signal. And so you can string a whole bunch of them together. And so the LEDs on the temperature thing are WS2812s, or NeoPixels as Adafruit branded them, and so everyone calls them. And they... I don't think I've sworn yet on a stream, Christoph, but maybe. They have their own protocol for driving them, and the protocol for driving them isn't great. But they're another example of this. And so they're easy to plug together, and you don't have to worry about killing stuff, and you get really, really, really bright LEDs. I actually think the LEDs on the color thing are going at like 50% brightness because they're too bright. These LEDs are a different example. There are other ones, like there's an SK9 something part, which was on the Chaos Communication Camp Watch, which is really cool. They're really straightforward to use. These are designed to use with a Raspberry Pi, and so we're going to use a Raspberry Pi today. I know I'm being cursed for even mentioning it exists, but we're going to try and do this on a Raspberry Pi. And what we're going to try and do is hack something together that will drive the LEDs and give us a color. I do not know if this is going to work. I have to find OBS. I have no idea if this is going to work. I had no idea actually how to drive these. I said at the start that I was doing this less prepared. And so to help me figure out what's going on is a piece of equipment I have liberated from work. I took it before the lockdown. I claimed I would have to do some design. There is some design to do. And so I have a very, I'm going to say it's a very high-end oscilloscope, but as oscilloscopes go, it's probably a pretty normal thing you would have on a desk as an engineer, and it's actually the low end of that. This one is souped up, so it has all the magical features, so it can do serial decode, it can do loads of other stuff. But actually, no, before I talk about the oscilloscope, let's start writing an SD card with my ThinkPad. And so I have an SD card, the camera's pointing away. The reason I'm not doing a top-down shot today is because I knew I wanted to point at the oscilloscope too, and I really didn't want to do a two-camera setup because while we got the camera going in the last stream, where on earth is the micro SD hole? There is the micro SD hole. While we got the camera going in the last stream, I'm not sure about the battery life on it because the battery's quite old, and it adds more stuff to the table, and less stuff is definitely more helpful if you're trying to do this. If you're going to stream, do what Christoph does and just stream a window. It'd be much easier. So we go to the everything window, and then I try and find my terminal. Come back terminal. Here's a terminal. Okay, so I am SSH to my FreeBSD laptop. I plugged in the card reader and an SD card. It says it's 30 gig, which is great. I downloaded this before. If we list all the FreeBSD stuff I have lying around, obviously I have tons of images, and then we do the nice high-risk command. We want the Raspberry Pi release. Can't type passwords when I don't say what they are. Hunter2. There we go. See, amazing. Amazing. And so what I'm doing is I'm DDing the FreeBSD 12.1 release image for the Raspberry Pi. I know this works because it's in another Raspberry Pi that died. It's not the image's fault though. The serial control node for my work testbed, it runs on a Pi 3 because I had a bunch of Pi 3s lying around, but the card is dying in it. I thought it would survive, and then I put it in the cupboard and it died immediately. And what we've done is we've DD'd the image to the card, and so DD takes an input file, which is the release image, takes an output file, which is the device. I've assumed it's the only card reader device in there. I mean, I know it is, but it's not. And then we set a block size and it DDs, and it's going to sit there for a while. And so while it sits there for a while, I'll happily take random questions, but I will try and talk about the oscilloscope. And we need to do some other things too. And I've hidden all of my stuff from myself because that's the sort of person I am. So this, let me see what OBS is showing. So we have a Raspberry Pi 3. It's a thing. They seem to grow in trees. People seem to have a lot of them. We have the Pi Minori board. It goes on the header of the Raspberry Pi one way, where the curves of the PCB substrate are. And if we plug this on here, this will be good, and it will plug together and it will work. But the problem with this is we won't be able to get a serial port on the Raspberry Pi. Oh wow, I'm making an assumption the serial port will come up in FreeBSD and Raspberry Pi. I'm pretty sure it does. But we need a serial port on the Raspberry Pi, and we also want to be able to poke about signals on the board to see where we're actually doing the right thing. And so to do that, we're going to use a breadboard, and I have to find the breadboard. And so to do that, we will need, you can go away, we will need one breadboard. I only have a giant breadboard, and then we will need so many jumper wires, you just will not even imagine it's possible to have this many. And so I have a bag of female ones, and I have a bag of male ones, and then the twisted nightmare mess of the male ones. And so we're going to use all these. We're going to use the oscilloscope. And so we'll hopefully get the Raspberry Pi awake. We can poke around in the oscilloscope. And then we'll try and get the board alive. And so let's check on this. The DD is still going. We hit Control T because we have a sensible operating system. Halfway. I can't just guess numbers like that properly. So what we want to look at is how these LEDs are actually driven and what they take. And the best way to do this is to find a datasheet. If I'd done status equals progress, it would have been really helpful. I didn't. That's quite new though, so I can understand not knowing it. We need to find a datasheet for the LEDs, and I promised in other streams that we will just look at datasheets because datasheets are fun. We can see I've already Googled for this. The results are not very helpful. If Adafruit have a datasheet, that's actually really helpful. One of the good things that Adafruit does is for all their stuff, they tend to put up datasheets and they host them again. So it's quite easy to track things down so you can figure out what they are. Somebody also wrote a blog post about these LEDs, and the blog post was very good. It might be this blog post. Yeah, it's this blog post. And so this blog post talks about more of what they are and how they work. And we're probably going to end up falling back on this because this is going to have a lot of Chinese in it. Oh, maybe it doesn't. It definitely doesn't have selectable text. This is just an image of some text. And so this is probably pretty normal for a datasheet. Normally a datasheet will tell you things that if you know what they mean, they make perfect sense. And if you don't know what they mean, they're impossible to use. I don't care about the process. Low voltage and low power consumption are interesting, but sometimes these are a lie. The LEDs like this they use in the CCC camp badge, they found that when they're set to 0, they somehow dump the full power's worth of current through the LED. I don't understand how they did that. And so they had to put a MOSFET in the power line so they could actually turn them off and save battery. Tricolor, 8 bits, 5 bits, brightness adjustment, built-in driver, which is what we expect. I don't know what self-signal detection means. It's nice being able to say to people you don't know what things are, and a lack of qualifications should mean that you say it more often so people will come and correct you. Continuous oscillation PWM. I don't know what that is, and hopefully that won't cause any troubles for us. What we're hoping for is that it's a nice, simple, clocked LED protocol, and it doesn't cause an absolute nightmare. And I'm just being distracted by the IRC. Oh, and there's a great comment from Warner in the Twitch too. It's good that it's all FreeBSD developers watching. You're not going to learn anything. Oh, and the image has stopped copying. So I'm going to bring up the Raspberry Pi because the sooner we can poke around in the oscilloscope, the more fun things will be. I had no idea what's streaming. What you really need for this are 800 monitors. But I have one, and because of OS X being very difficult, I have to use 2 laptops. So I think the simplest thing to do is to get the Raspberry Pi to bring up the most annoying SD card slot in the world. Get the Raspberry Pi to come up and then start faffing. So there is an excellent website called pinout.xyz. It is a great website. It tells you where the pins on the Raspberry Pi are routed to and what they do. And it is also a real good sign that their documentation is appalling because there's a website, which is a third party, which does this. And it gets enough traffic that they have a Patreon. And they're probably struggling for money. And so we need a ground. The third pin down here is ground. And then we're looking for RX and TX on the Raspberry Pi. And I sort of know where they are anyway, but we can see them. They're on... it highlights on my mouse over. They're on pins 8 and 10. 7 and 9 are on the other side. And then I have to look at this stupid USB serial thing and find... Okay, so it says RX is green. It won't be. Okay, connecting that up, and then plug this. As we've done in every other stream so far, I'm going to connect over serial. The baud rate for the U-boot on the Raspberry Pi is thankfully the same Hunter 2 as everything else. There's a nice common point. It's not the fastest baud rate, but it's a nice common point that it makes it easy to figure out what things you're going to do. And now I need power. This cable. Well, it would help if this wire was plugged in. So, nothing. Why does nothing happen? There is power. There is an SD card. There is a USB serial. We're connected to it. Raspberry Pi default baud. That's not very helpful. First answer Google. None of these are helpful answers at all. Let's go for a different sort of question. On the Raspberry Pi 3, they changed the routing of the serial port. So the Raspberry Pi 3 added a Bluetooth module. And so the normal serial port, they routed to the Bluetooth module to do Bluetooth. And then they've routed a different serial port to the pin header. I feel like I don't think I'm guessing. It feels like a real memory. 115200, so it's not that. I don't need to find the name of the serial port on my PC because I found it. So there's two things. It could be that the Raspberry Pi is not happy with the power. It could be that the SD card did not write. I can try the SD card on the ThinkPad, and we expect to see FAT32 boot partition. Which we see. It could also be that the USB serial is not actually connected. So when things do not work like this, what you need to do is unplug everything and try again. Because OBS doesn't like me doing the Mac Zoom thing, I understand. Because what you can do is you can make a silly assumption that you are correct for something as simple as putting an SD card in the right way, which I think I have done. You can make an assumption that you're correct and not be, and spend a lot of time working from a bad assumption. So we look at this website. The pinout does not change between Raspberry Pis, apart from maybe very, very old ones. So ground is on the third pin header here. It could also be I don't have a good ground connection because these jumper wires are a bit loose too. And then we're going to go TX, RX, and we'll double check. So we missed the first two, the top of the pin header. We have the next three. And I'll disconnect this from my ThinkPad. And so the far end here is ground. And then we have TX as the top one, which goes to RX. And then we have RX as the next one, which goes to TX. Connected together. Okay, that's happy. Power into the power hole. Green LED blinks. Nothing. I don't really want to spend forever debugging this. This would be very easy to debug with a monitor, maybe. So this is me not trying things in advance. This was probably the obvious one to try in advance. And so what it means is today we're not going to be able to plug this onto a Raspberry Pi and have it do the right things, but we can just use another single board computer because I'm inundated with them. But I think I have to go underneath the table to get it. Oh, I should have muted when I did that. Okay. So instead, we will use our friend, the BeagleBone Black, because that at least worked last week. We'll use the USB on the go on it. I actually wiped the SD card on the BeagleBone Black for the Raspberry Pi, because I have a shortage of SD cards that are alive, because they like to die, and Raspberry Pis like to kill them. So let's see what is in my downloads folder and see if it is useful. Oh, look, there's a BeagleBone Black image. So let's do that again. I normally wouldn't give up when USB serial doesn't work like that, but it doesn't make a compelling stream to watch me sit here confused. And I could have showed off and I could have proven to you that the USB serial was generating packets by using the really fancy oscilloscope, but it doesn't actually help anybody other than me. Okay, now while that DDs, we'll go and try and look for this datasheet. This can go away. It would also be very funny if we find out that the SD card just doesn't work. But the SD card was written to and it seemed okay. Okay, datasheet. Datasheet tells us pins and pins out. And so the APA 102 has 6 pins. It has a DI and a CI, which are data in and clock in, and a ground on one side. And then it has a DO and a CO, which is data out and clock out. And then it takes 5 volts on the other side. So it's a 5 volt device. Weird. I guess it doesn't care very much about the signals it gets, because the GPIO on the Raspberry Pi is only 3.3 volt tolerant, and it's the same on the BeagleBone Black. But the supply voltage can come from somewhere else. I've had issues before with the supply voltage on the BeagleBone Black, but some of them are not all of them are the same, and there's a lot of pins, and so it can be trickier to find. This 6-pin layout, like this, with the VCC over on the right, makes doing a PCB layout really annoying, because if it was like an 8-pin where the VCC passed through, then you could just lay these out in a nice row, and instead you end up with weird loops to get VCC all over the place and ground. There are some words here. I don't know how important they are. And there's 15 pins. I'm just going to ignore it. Datasheet has a block diagram. They have weird things in datasheets. Yeah, maximum rating, input voltage, temperature. Lots of these you can just exceed. And so there is a minimum oscillator frequency. And the minimum oscillator frequency might cause trouble for the thing I want to try and do. And then we have the data layout. This is actually quite a good diagram for data layout. I wrote a shell script to drive, what is it, a P983, which is, it's like one of these LEDs, but it has a bunch of MOSFET lines, so you can drive higher power things. And basically all of the pictures in the diagram were in Chinese. And so it's very difficult to figure out what's going on there. And so this diagram basically explains what we need to do. And explains what on the wire we need to construct so that we will drive the LEDs. And it does it in 3 parts, I think. So we can drive probably as many LEDs as we can practically put together. I wonder why it's called a date field. There is a start frame. And a start frame is the bus held low for 4 bytes worth of data, or 4 chunks of 8 bits. And then there are 1 to n LED frames. And so the LED frame starts with, so there are 5 bits, if we scroll up. There is a 5 bit, so a 32 level brightness adjustment. And so we start with 3 high bits, And then we have 5 bits, which are the global brightness, which applies across the RGB. And then we have 8 bits, and it goes blue, green, red, which seems fine. And then I don't know what this last LED frame refers to. Oh, okay. The last LED frame is basically any frame which is set to all high indicates the end of sequence. I don't know if that means that if you send a frame which is a start frame, then the end frame, I don't know what happens, but we just won't do it. It'll be okay. So the first two are very easy for us to put together. We're going to work from a shell script I wrote before, once we have a single board computer that works. And the LEDs, they seem fine actually. I don't think there'll be a problem. Okay, this says it is done. So let's try for our next single board computer. I have more. We can just go through the list until one of them works. Let's put the SD card in. When they introduced the Raspberry Pi Model B, they said we got rid of the ping and fling style micro SD card thing where you can put it in and it pushes and it pops. And so the ones in the Raspberry Pi, you just push in and they sort of stop, and I hate them. Awful choice. Okay, the Beagle One Black is alive. It's plugged into my laptop and it's getting power from my laptop. Also, as we saw last time, and I really hope so today, we should get the USB on the go for the USB serial port to come up, and if not, we just plug the FTDI in. That will take more mini USB cables. Yeah, switched RX and TX, and it didn't help. It's funny as well saying that. So in the tutorial I did last year, and I'll hopefully do again, I was like, if it don't work, just plug the wires out and swap them over, and everyone laughs. I'm like, no, it is the only advice. There's nothing else. I mean, you can poke it with a multimeter, but the point where you have 3 cables and something doesn't work, you're in trouble if you don't have if this is the end of your approach. But as it was, I mean, we're done. I don't know. Maybe the images we're producing right now don't actually bring up the USB serial. I know people don't really care about the Raspberry Pi 3. It works on the one I have in my the serial node in my test cluster has a screen on it, so I see the screen come up. It could be as simple as that. The screen on it is not a HDMI screen. The screen on it is connected through the weird video port they have, which means it is no good to go and take and use over here. Let's look at dmessage. It's gonna be one of those days, isn't it? I just keep typing the same commands to see if I get what I want. You're alive. You're plugged in. I'm on my laptop. Okay. I have to stand up to get the 800th mini USB cable. Okay, it was unhappy, and that's why it did not come up. Great, and it boots now. Another option is always to turn things on and off again when they don't work. I'm not going to worry about it. So this is what happens when I don't prepare, is we spend 40 minutes where I try and turn things on and me blathering about what they could be. I am planning to go for longer today than normal, but I'm not going to go for more than 2 hours. So we will see if we actually manage to do anything with these LEDs. And there'll be another stream if we don't, for me to try and drive the LEDs, because I thought I would try and do something a bit more off the cuff. We can see how well this is going. You'd easily spend hours doing this. This is what all of computers are, but this is particularly annoying with hardware stuff where you really can just be staring at some wires you plug together and it not work, and you have no idea what's going on. Also, there's no get revert. So when something explodes, you are sometimes stuffed. I try not to fiddle with the case of the BeagleBone Black underneath the microphone, because that's just annoying. Yeah, and so now in the D message, so I SSH to another terminal, we have the virtual serial port. So we can go back here, and instead of logging in, we can hit tilde twice and then full stop, so we don't disconnect our SSH. And we can connect to port 1, and after a couple of taps, it will come up and be alive. And so that's good. So we have gotten somewhere. Now, the BeagleBone Black, I cannot remember where any pins are, and there's not a helpful website like pinout.xyz. Instead, for the BeagleBone Black, we need to go and find the technical reference manual for it. We want the technical reference manual, and we want the PDF of it. The TRM for the BeagleBone Black is very comprehensive. One of the best data sheets I've ever seen. It actually includes stuff. It's because it's open to the community and people can dig around, and TI are actually quite good about this. It's also giant, and it doesn't have a table of contents. That's infuriating. We want to know the pin out on either the P8 or the pin 9 header. We can actually Google for BeagleBone pin out, and we can get a reasonable diagram for it. Let's see if disconnecting the USB serial killed anything, because that would also be an annoying setback. Still alive. Root. Default credentials on the images we produce. And so we can click on this. The annoying thing about these diagrams is they never include the serial cable, the serial port I just used. This picture we're looking at is the one from the TRM. The string P9 is not great to search for in a document, but gpio 117 might be okay. Yeah, OBS does tax the MacBook quite a bit. Oh, apparently it doesn't exist. This is the problem with PDFs as well, though. Where are you? I want one diagram. Oh, okay. It's because this is not the technical reference manual. It's the system reference manual. I'm sure they called it the TRM. This is really annoying. Anyway, we'll look at this picture. This picture tells us what we want to know. I don't know where the top of the headers are. Oh, okay. They helpfully label the pin numbers on the headers. And so the first thing we want to do is find an available GPIO and just toggle it. No, let me focus. So before I did all this faffing, we were looking at the bit pattern for this. Helpfully, Pymonori, they provide a Python library, which they link to. Oh, I missed something. They provide a Python library that they link to. And in their description of the board and how it is connected, they give away something. And so they say here that here the data and clock lines are connected to GPIO 23 and 24 respectively, but for simplicity, blah, 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 you can use the library. And so if we look at the pinout of the Raspberry Pi and we look for 23 and 24, we find them here. So there's pin 16 and pin 18. Oh, cool. That's a nice dialogue. These pins are not routed to the SPI interface on the Raspberry Pi. Pins 3 and 5 are routed to the SPI interface on the Raspberry Pi, which means, no, not those. Pins 9 and 10 are. Oh, they're right next to each other. Are on the SPI interface. SPI is a serial bus. The serial bus always looks like a clock and at least one data line. Sometimes it will have bidirectional data lines. And so these LEDs, they look like SPI. Now, I don't know if you could drive them from the SPI hardware, you should be able to. But if you could drive these from if these were connected on the status thing to the hardware, then it'd, one, probably be quite easy to drive, and two, would use a lot less processor to drive. So updates on this probably take quite a lot of CPU to do. Because we have backed ourselves into a corner and we don't have the Raspberry Pi to use and Linux to start from a reference, we can instead look at their Python library. And so this is actually what I plan to do. They make a Python library available. It's not been touched for a while. I actually used this and Linux over Christmas to make a fireplace out of one of these, and then something called like a PiBo Mini, which is a WS2812 screen. The fireplace looks really good, and I left it burning at work. So I have contemplated every so often if security wandering around at night and they think there's a fire in my office. So what I want to do is I want to find where they drive the GPIO so that we can copy what they do. And this is where they drive the GPIO. It's very straightforward. Yeah, I mean, it's a 160 line Python file, so it's very minimal in what it is. And it offers the API and then how they drive it. And so we are going to do something similar to this. I think I have to find a shell script from somewhere that does something similar. But let's find some GPIOs that work on the BeagleBone Black as our first step. So what we'll do is we'll find some GPIOs and I'll show you them going on the oscilloscope. Hopefully the camera is not going to die before we can do that. I might actually turn the camera off. I'll turn the camera off. I think it only has like an hour worth of battery because it's quite an old battery. We will try that. We'll drive some signals and we can start making a signal which actually looks like the right thing we want to do using a GPIO. If you have an oscilloscope, then this is a very straightforward thing to do. And if you don't have an oscilloscope, you can do something like you can debug this using LEDs or a multimeter, because the first step you normally want is to just get any signal out of the board. The same way as if you were approaching a big code base and you had no idea how it worked. One of the things you might try and do at first is just get a print statement to come out. And normally getting a console log coming out of something is a great way to figure out what the logging infrastructure is. If things are common sense to how you think they should be. And Hello World for any hardware project is blinking an LED. And blinking an LED is just toggling a pin high and low every so often. I'm looking for a brown jumper wire and a bag of jumper wires, and I don't have any. Let's go for purple or black. There's a black one. Like my soul. While the colors of the pieces of metal you use to plug things together don't matter for the circuits you build, they do matter for your ability to understand what you have done to yourself. And so it is good to at least try and be consistent. Okay, so we look at this header. We need to find for the blinked, we need 5 volts. We need 2 GPIOs, which are not being used by anything else. And we need a ground. Oh, all of the GPIOs on header 8 look free. I think that is a lie. I think most of the GPIOs on header 8 are actually used for LEDs. And if we look at another picture, we find that almost all of them are marked LCD data. I know a way that we can find free GPIO pins on a BeagleBone Black, and that is to look at the FreeBSD journal. For 2019, I think it's 2019. Because someone wrote an article using the BeagleBone Black a year ago, and it was in the FreeBSD journal. This is not the FreeBSD journal's website. No, I don't want to do a tutorial. I couldn't tell you who it was, though. I went through all of this. Look at that lovely picture. Look at all that. Look at that table that was in the last place I lived. Okay, it was the SRM. Why did I pick those? Okay, so the gray box here, I don't know if my mouse pointer is coming through. The gray box there are the 4 LEDs on the board. So let's try turning on one of those. The GPIO signal name tells you which bus they are on. Because the BeagleBone Black has an absolute ton of GPIO controllers. So if we do... We have 4 GPIO controllers because there's a lot of I/O coming out of the BeagleBone Black, which is why people like doing hardware stuff with it. I'm gonna have to check OBS to see if I'm actually showing you anything. Oh, and the camera just froze when I killed it. But it's actually quite good. So this isn't. I'm putting my hand in front of it to show you can't see my hand moving, but I was moving my hand. So there are 4 GPIO controllers. No, I want the terminal to be able to be clickable. There's 4 GPIO controllers. And the table I took from the SRM, I'm sure they call it the TRM, from the SRM shows you which pin, which is the thing after the underscore, on which controller it is. And they have something else. So FreeBSD, as we did in the past, we have a command for GPIO called GPIO control. None of these are on the default, which is GPIO C0, so we have to pick one. List what's there. Which pin do we care about? 21. 21 is marked as an output. So if we do our previous command and we toggle 21, I turned the camera off. Let me turn the camera back on. I think I'm going to have to restart the program that does the video too. Kill you, start again. Okay, so we have here, which I just turned on, we turned on user LED 0 using GPIO control with the toggle flag. So we'll just turn it on or off based on whether it's on or off. And it just I typed too many keys, so I can just toggle that. This is great because there are 4 LEDs here, so this could actually give us status if we want to tell us what the board is doing. We want to find GPIOs which are actually available, and I think I covered that in the article too, because I needed to write 4,000 words, and you had to do slightly more. And that's the GPIO controller I picked before as well. This says some more stuff about configuration. The configuration is actually the default we wanted, and so on the I can't tell what the diagram is showing. Oh, so on the P8 header, there are 3 GPIOs that I picked, which are consecutive to each other, and I made a nice little diagram using fritzing. And so let's just go for 2 of those, and let's get a signal, and let's get something coming out of this port, so we can say we've done something. I'm going to run all of this through the breadboard to aid our ability of plugging more wires together in the future, because we're going to need more wires. And speaking of more wires, I had to reach down and get more wires anyway. So we need 2 bits of wire can go away. So we have a green wire and a blue wire. I'm going to count from my picture to find the correct pins. 1, 2, 4, 5. So from the 7th one down, including the ground I've already plugged in, we should be okay on the P8 header. 1, 2, 3, 4, 5, 6, 7. Yes, counting on your fingers is encouraged when you have to deal with hardware. While you still have fingers and you can still count. Let's plug them onto the breadboard in an order that will give us sensible results in the future, though. And so all I've done is just plug these into a breadboard. A breadboard, I have another one, but I will flip this one up. Breadboard has basically like jaws that go up and down across the board. And so apart from the gap in the middle, anything going across the short side of the board will connect together. And it makes it easy to plug together circuits quickly so that you can just play with them. And then I'm going to add a green and a blue jumper wire so we can connect them to the oscilloscope. And I guess I need to find a black jumper wire. Green and blue. And a black jumper wire. That would be nice and consistent. And keep the ground further away so that I don't pick up the wrong thing when I want ground. And so, because we're not going to have anything connected to, yeah, I shouldn't do the zoom effect, it ruins it. Because we're not going to have anything connected to an output. So in the article, I used LEDs and resistors to limit the current. Instead, we're just going to connect this to the oscilloscope, and so we can just connect it to the oscilloscope. And I now need to figure out how to reframe this so we can actually see most things at once. That was the wrong zoom direction. So this can be brought up. So for some reason, yeah, okay, we're not getting the big open black at the same time. For some reason, the live display is not coming out on the camera. So maybe that'll help the battery life. So this is here, just hidden. And what we need to do is to acquire oscilloscope probes from the mess of oscilloscope probes. This is technically how you're meant to store these. I have no idea. It's how we store them at work. This is a great oscilloscope. I actually love these things, and they're completely beyond anything I could buy at home for my own use. The sad part about the business model that Agilent have is that you have to buy the functionality which is already shipped there. These are basically a Windows PC. I think they still run Windows CE and an FPGA. The FPGA does sampling and it draws directly into the screen. And there are loads of great videos online about how they work and how the engineering goes for them. But things, sorry, I knocked the microphone. Things like serial decode. So if I press this button, which I get serial decode or the digital mode. Okay, I have to disable serial. Go away serial. Digital mode, which gives me 8 more channels, are add-on features, and so is the network interface on the back and the VGA interface on the back. The VGA and the network are they're also physical modules. Oh no, this is a green label on it. Anyway, I'm going to be really confused later why the green wire is not green. And they're add-on modules. And so like the hardware ones make sense for them to cost more money. The software stuff is quite annoying. And it's really annoying when you're setting up a classroom where you have to go and add like £1,000 worth of licenses for things that the oscilloscope does. It's just missing a piece of paper. And I know this is how they do the upsell, but in 2020, it would be quite nice to be able to say serial decode is a standard feature on high-end oscilloscope. And maybe the cheaper model you might buy for use at home won't have it. Because we use it in our teaching, because we talk about communications protocols. But it's not what we get. Okay. I will reframe to show you, and then I will go back to the... So what I've done is I've connected 2 probes. One probe is grounded, so we have a reference for the scope. The other one, I don't care. They're connected to the breadboard. They're on jumper wires. The one with the green label is where the blue wire is, so when I get that wrong, that's why. Come back. No, all the way up. Try and get my bagging link to focus maybe slightly. No, okay, that'll do. I don't care that much. Okay. Camera, please do not die now. So what we want to do is we want to drive these GPIOs. If we look back at the article, we have 3 of them defined. I wonder where that shell script is. So the easiest thing to do would be to copy a shell script I've already written. So if we take one of them, so the GPIO 026, and we set it to 1. No, because you can't do... Oh, okay. So the first thing we need to do is we need to actually look at what these GPIOs are set to. So pin 26 on GPIO 0 is configured as an input with a pull down. I don't know if we care about the pull down, but we're going to configure it pin number as an output. So we've changed it to be an output. And now what we can actually do is we could toggle it and we'll see if anything happens. And I need a pin number to toggle it. Okay, so that worked. It flew off the screen there. And so there's nothing to see. But what we can do is drop into our real shell where we can actually program. And we can do, while on tour, while true, remember how to type. Okay, and if I bring up OBS, what you see on OBS is a line jumping backwards and forwards on the oscilloscope. If I change the time base on the oscilloscope, and maybe if I move the signal down a little bit, we're at like half a second, so it's not very happy. Render, so we see an edge, and if we let it catch up, I can move this signal down. And so what we have from the true loop, so I wrote a infinite loop. It loops, sleeps for half a second, and it toggles the pin in between it. And this gives us a square wave. And on the first guess, I got the right pin, which is pretty cool. Nobody ever would have expected that. I was being spoken about, not to, so it's fine. We need to find the next pin. So if we go for the obvious one, if we go for 1 and 14, oh yeah, because it'll be the next pin. So we need the other. We need to configure the other one, which is pin 14. And then we do both at once. Yeah, okay. I can make these both the same size. Move you up, move you down. And because I very helpfully did this before, I was trying to not do things before, but because I very helpfully did things before, and if we check on OBS is still alive. What we have now is we have 2 square waves going in sync with same. And that is actually what we need to do. So if we look for a helpful reference on the internet, maybe this one will be a helpful reference on the internet. No, there's a lot of words here. Oh, that's cool. No critical timing. If I Google SPI, let's see if we can get any nice images of a capture of an SPI. I'm not getting any nice images for a capture of an SPI. So, lots of pictures of noise. Lots of noise. So the SPI, it has loads of bits to it. It is simultaneously referred to as 2-wire, 3-wire, 4-wire, and 5-wire as the same thing. Really, it's the SPI. The features of SPI that make it SPI are that there is a clock and the data is clocked. And this is different to a UART or a serial port that we're using, where it is implicitly clocked, so there is a fixed rate. In SPI, you find, I think, the rising edge, and then after the rising edge, there is a time at which you can look and the data will be valid. And then there's a falling edge, and there's rising edge, and you get valid data. And so the picture I found is not somebody trying to debug it. It's probably something you would expect from a datasheet. And so what we have, this is more of the wires, so this would be like 4-wire. There's a chip select line. We don't need to worry about the chip select line. All we have is a clock and a data line. And so with each clock pulse, data comes across. Now, SPI can run bidirectionally, and so you'll get data returning because the slave device will be sending data back to you. We don't have that. We only have a write-only device. The LEDs aren't going to tell us anything. And so if we can clock data, and if the clock doesn't need to be too fast, we should be able to, from a shell script, format the data so that we can drive the bus. And I have done this before for a different sort of LED controller, 9813. So these are a really interesting little driver. These are the sort of boards I have. They are effectively like one LED in an LED strip, but they're a higher power device, and so they chain together the same way these LEDs that we're going to look at on this blinked thing. They chain together the same way, but each one of them is basically like one LED. And in this layout here, there is the chip, and there are 3 MOSFETs, so they only give you 3 channels. The LED strips are normally common anode or common cathode, which means one of them is a common, so you connect the commons together, you get the LEDs to come on. These do not care about timing at all. I have blog posts that I've never published because I've never finished doing it, but I've written about these before. I used them for a light box. I took all the photos for the tutorial last year, and they take in serial data. They get a start sequence, they take in serial data, and I think it was maybe a stop sequence. And so we're going to start from this script I have to drive those, which is somewhere. I don't know where. It's just somewhere, and we'll modify it because there's loads of bitwise operations in the shell script, which are not things I ever want to do again, but because I can copy them from somewhere in the past. So I am going to go and try and figure out where they are in a different window. So this is just going to be off screen for a minute. I think Warner is upset by the prospect of me bitbanging a protocol from a shell script, and he's right. He should be. Yeah, so I'm going to copy and paste this. Come back, find this terminal, kill this, exit the good shell. And so I'm going to call this. I don't have to use set paste. And so here we have a shell script. I'm going to move slightly over so I can actually read it. It takes hexadecimal colors, and then it figures out what the bits should be, and then it shifts them out. It doesn't go very fast. There's a delay in here somewhere. I don't know how low our sleep can go. I don't believe that this is going to work for anything other than the P9813. I have the equivalent C program because I wrote it in C first because I was very worried. I was very concerned about the ability of this, but it turns out it all works out okay. And that is the pleasure of dealing with something which actually does SPI, is that it will, because it has an actual explicit clock, it doesn't really care about the timing as long as it gets the correct bits. And so we need GPIO 026 and 114. I clicked the wrong window. I want my terminal again. So we helpfully have these as variables. So we want 026. Oh, it's it's like the defaults here were almost for the defaults. I did this on the Pocket Beagle, I think, because I wanted to play with that, and so they're maybe actually what those pin numbers are. So what we're gonna do is run this script, and it won't complain because I didn't care about error checking. We send it 6 zeros. Nothing happens. Don't you hate it when nothing happens and you expect something to happen? So the future we live in, if you ever were shown an oscilloscope in high school, and if high school was a long time ago, and to be honest, if you were shown an oscilloscope in high school today, it'd probably be an analog oscilloscope. Yeah, okay, so that worked. Analog oscilloscopes are a thing. They are not a modern tool in any way. This is what you might call a storage scope, but it's sort of a silly thing to say because every oscilloscope now is a storage scope, because I don't know how you build a digital scope without storing stuff. This means that I can, which I've now done 3 times without saying, is I can start and stop time, and I can control how signals are. The oscilloscope by default is set up to do like an edge detection on probably the first input. So it can do triggering based on signals. This oscilloscope will do triggering based on up to a 2-byte sequence over a serial line. And so when we teach DMX, we use the triggering so that we can give a student somewhere on the bus and they can see what's changing. So I pressed a single button. It means the scope will run till it triggers, and then it will capture a buffer's worth of data and it will show it to us. So if I run the script again, you see it drawing out very slowly. And what we've got is we have the clock line, which is in green, and we have the data. This comes through, and we can actually play this back, and we can play it back at different times, and we can zoom while we're playing it back so we can see what's happening. The thing that throws people when they're learning this is that we have a fixed amount of data the oscilloscope will capture. This is 2 gigasamples, and so if our resolution is out here and we do a capture, this will take a long time. I did not think this through. Oh, sorry, I knocked the microphone. Let's take this to 5 seconds. Do that again because it was going to take forever to draw. We zoom out really far and we look at a higher frequency signal. We get fewer samples to look at the signal. And if we zoom in, we get more samples. And so triggers can help us look at something very precisely and see if it is a mess or not. And I have no ability to do analog electronics at all. Not dribbly, just accidentally know things. It says it's triggered. It didn't trigger. Oh, there we go. So it's drawing. Once this draws through, you can see that, hopefully you'll see that the resolution is a lot worse. I'll do a zoomed in one as well, because there's a fixed number of samples being captured here. So you see the whole clock pulse that we had before. Oh, God. That is not what I want to have happen. Okay. I don't care. So I'm going to zoom in more. We'll look at a higher resolution one. Okay, it's coming through cleaner. So we can zoom in really far and we get a nice clean signal. If we have a higher speed signal, we're not going to have a higher speed signal. But if we did, we could look at this and we could see actually get better captures. And this is cool. Anyway, I like oscilloscopes too much. It's mostly because they're completely out of my price range and impractical. Though I do have a cool Bluetooth one appearing eventually from a Kickstarter, like the one George has. So this shell script, it takes in a color in hexadecimal, like you would for the web, which is nothing like how RGBs reproduce color. And it forms the bit pattern for that. Maybe I'll show you a different waveform actually. So yeah, a second is okay. So I was showing the output for all zeros, which is less interesting than if we do like FF, AA, EE. If we do that, then we get more bits coming out. And so we see more. So the top line is the data, and then the bottom line is the clock. So the clock is basically fixed. And if we put in other patterns, like 1, 2, 3, because I need 6 digits. Well, and if I do that again and actually show it, it didn't get any more interesting. The P9813, which is what this is written for, and it does drive properly. So this is not a completely crazy idea. It did work in the past. It sends a start sequence and a checksum. And so this, the checksum is made of a fixed byte sequence and then the inverted values from the 7th bit of blue, the 6th bit of blue, the 7th bit of green, the 6th bit of green, the 7th bit of red, the 6th bit of red. So that is, it sends a checksum, which tells you what the color is. Yeah, okay, it does 4 zeros, checksum, color, 4 zeros. And so I think, and then the net, if there's not 4 zeros after that, it looks at to see if it is a checksum, and then it sends that. And that's why these are knotted, I think. We don't seem to need to do that for the APA 102 from the datasheet. From the datasheet for the APA 102, we need to send 4 zeros, a color, and 4 ones. And so we could just, maybe we could just send all the bits set. Maybe I'll set, if we send a color which is off, it'll be very difficult for us to tell if we've actually sent anything at all. And so we can set this up so that we can send, maybe just set the first 2 bytes just all high and the next 2 all low. And that should give us a bright blue and a bright off green. And you know, a bright dark can consume the light around you. So we'll be careful not to kill the lamp. And then we need to send 4 bytes of zeros. So that should be straightforward to do. Sorry, I keep doing the zoom effect because I do it all the time. This debugs and tells us what the pattern is going to be before it sends. I keep trying to hit Shift V because I want Vim. And so let's copy and paste that. So we want, oh no. Four zeros. So each number here is a byte. And so we want 4 zeros and then 4 ones. And then we don't want any of these. Normally I would press V and we'll hold down X. VI is confusing. F. I wonder if these work in hexadecimal. The problem with shell scripts is, so that's not what I said I would do. So we're send the, oh, that's not a byte either though, is it? I don't know if this takes, if this will be happy with Fs. Let's just try. So what we do is we send the zeros as in the datasheet, which is the start frame. We send the ones, which are the end of frame. And in the middle, we're just going to send 2 bytes high, 2 bytes low. And so we can, oh, sorry, I knocked the microphone again. So this is the problem when you put too much stuff on your desk. So I'll bring this back. So the color we send now is independent of what we actually send as an argument because it didn't, because we're just going to play with this to see if we can get color of it. Is that what I expected to happen? It might be. So if we zoom in, no. So I wonder what's happening there. This is a problem looking at the shell script you wrote a long time ago. So there are commented out echoes here, which will tell me each bit as they get shifted out. But then the rest of the shell script sort of descends into madness that shell scripts descend into. And a big problem when you're dealing with hardware is you end up looking at a lot of hexadecimal sequences and shifts that are they're very difficult to look at in the future. And if you worked on an operating system like FreeBSD, you would use nice constants for some of these. And really, that would be a way you could judge the quality of a driver, is how much of a nightmare it is to look at again in the future. It doesn't look right, though. The bus shouldn't have been left high, I don't think. Not what I meant to do. Oh, no, it is. Okay, yeah, so the bus, but there's no clock. Yeah, so the thing that's confusing me is that the clock line should still be going when this is high. And so I wonder if it's because there's something special here that I can't remember how it works. You wouldn't think there would be anything special in a 50-line shell script. It could be very easy that 1 and 0 are swapped here as well. Let's try using numbers in decimal, because that might be the thing that is throwing the script off. So that is almost what I expected to have happen the first time. So if we look at the yellow line, the bus is held low with the clock going, then it goes high, and it goes high for a while. We could measure this, but I'm not going to. I don't understand what these extra... Okay, and then there are 4 pulses at the end. The final pulse, the bus is held high at the start. We bring it low when we're writing, and then it goes back to being high again. Okay, it makes sense. I now understand. And so these ones here, this should actually be 1, 2, 5, 5. I think that's what this should be. So in this pattern we make, the 4 0 bytes are what we want, and then we want 4 255s. So okay, so we have 6 255s. So I'm going to change these to... I'm going to change one of them to 85. What's the other number? I'll change both of them to 85. 85 is a repeating on-off pattern in decimal. This is not the sort of thing I would expect anybody to know, but it is one of the trick questions we try on students, so they can decode numbers. And we see a repeating bit pattern, and then the bus goes high. If we look at this blog post, the blog post might just show us immediately what we should do. It goes high, goes low. You could always do more pictures on your blog posts. I'm very impressed actually that the camera is still going. So oh, that's really helpful. Thanks, Warner. I'm not going to modify this shell script right now, but I think I will keep it in mind for when I'm inflicting awfulness on students, because what else are you meant to do? Sometimes, Alan, you can use I don't know if Alan is watching. Sometimes you can get around a lot of these issues with printf. Annoyingly, our printf doesn't support hexadecimal formatting. It only does octal. And so I think there is actually a step of octal in this. No, we might be safe in this one. There might not be any octal in here, but octal as a middle representation is really confusing for people who've never used a PDP-11. So I'm happy that we can form the correct bit stream to send to these LEDs, and I can't think of anything else to do other than to connect it up, because there's a sort of seat of the pants magic we need to go for. So there is a ground that we're already using at the top of this, and it's a ground on the breadboard. We need to find a 5 volts. There's a 5 volts on the other side. System 5 volts means that it is coming from before power regulator. So, as he says, we should be totally safe to draw all the current we want from there. There shouldn't be any trouble at all in just drawing tons of current. And to be honest, if I kill this BeagleBone Black has been going for so long, I wouldn't be so concerned. So I need 4 wires. Oh, look, there's a green and a blue one. And then I need to find a black wire in this bag. I'm sure the bag doesn't sound great if you can hear it. And if you can't hear it, you don't know what I'm complaining about. That's a tiny wire. Well, purple is basically black. So that will do. I have an interesting question that I hadn't thought of until now. I do not know where to... Oh, okay. No, it should be easy to find out where to plug in the power and the ground, because they're either all connected together or none of them are connected together. And there's an easy solution to that, which is to poke it with a multimeter, which is what I will do if I don't get anywhere very quickly. The green wire is the clock, so we need to find the clock. If we look at the product page again, which was far in the past, data line is 23, clock is 24. If we look at pinout.xyz, we find 24, which is pin 18, which is 9 down. I could have done that in my head, but I didn't. 9. This is clock, and so the one above it is going to be the data, which will match the colors we used before. I'm going to assume there are only 2 5-volt lines on the Raspberry Pi. I'm going to go for the top one. It's not very strong bonding there. And then I'll go for a ground. And so, where on the BeagleBone Black is this thing we want? The 4th pin down is a system 5 volts on the inside of pin 9. 3, 4. That's the only one we're plugging directly to the BeagleBone Black. Our purple one needs to come to ground. And then, in the grand tradition of being consistent over time, blue goes to blue and green goes to green. And nothing has happened. So that might mean that when it powers up, nothing happens. It might mean that nothing is going to work. So we will run the scope to make sure our signal is a signal. This repeating pattern we're sending is not correct, and the scope did not trigger. Interesting. What did I break by plugging in wires? Yeah. It's always fun when you do something which you expect to be completely innocuous and nothing works. The BeagleBone Black is alive, so I've not shorted anything. A nice sign that you have shorted something on a single board computer is it turns itself off. Sometimes it does it permanently, but sometimes it just does it for a short while. The oscilloscope is normally the common consistent working factor. I'll disconnect this power. See if we can get the scope to trigger again. Okay, so that power is not doing what I thought it was. Some manufacturers wait, there we go. The blinked pinout. There's a picture. Okay, it uses the 5-volt line I did not use. Some manufacturers provide schematics for the things they make. And they really help when you're unsure if something is working or not to have a schematic to verify against. I'm going to go for a different 5 volts this time because I want to. Okay, and the LED came on. Who expected that? I'm actually stunned. I was not expecting it to work. That's good though, because that proves that I'm not a crazy person, and we can do whatever we want. And so let's modify this to do it for 1, 2, 3, 4, 5, 6, 8 LEDs. I don't understand what we've actually sent. I think that should have been what we sent. Wait, no, there's too many, aren't there? There's 1, 2, 3, 4, 5, 6. How many bytes do we need to send? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I think that worked from a complete fluke. I don't actually expect there to be any change by me running that command. Okay, I disconnect power on the LED. Try not to nudge the camera too much. Run this again. Okay, the LED came on. Oh, I don't know if last time the second LED was on. That's annoying. And the scope didn't trigger, which is fun. That does just happen sometimes. And it could easily be that I notched something. But we've got that LED coming on, and we've got it coming on with some sort of color. But we don't know what sort of color. I genuinely... Okay, wait. So... takes the colors, figures out a checksum, and I think it turns the colors into... I think it turns the colors into decimal for what we need. And so we'll add a variable called brightness that we're going to set to... I'm just going to start by setting it to something with every bit set, so it's always as bright as possible. And then we'll add blue, green, red. This order of blue, green, red in both of these, so the P9813 and this, to be honest, I think to me is revealing probably internals of the hardware and how they shift in colors. So now it matters the color we send here. And now we have 2 LEDs turned on, which is definitely not what I intended to do. Let's run the same thing again and see what we get. Okay, so it could be that noise came through. Sorry. So one of the LEDs turned itself off. It could be that we got some noise there, and that's why the second LED came on. The easiest thing to do is just to kill the power to it. So I'll kill the power to it. Go away, plug you back in. And we run that command again, which sets them all to 0. If the LED comes on, it's a sign that there's a problem with our bit pattern. The LED didn't come on. We set it to that again. Yeah, we got 2 LEDs. So we are not sending the correct pattern entirely to this LED. And that's expected, right? I mean, we didn't actually do very much to get to the point where we're turning an LED on. And we don't seem to have any control of it either. So let's edit this script so that we don't send the brightest color possible. I want to write hexadecimal and I can't. What is the number I want? Here we go. I want this number, 240. I don't think I want 240. I want this number. I think I want less bright than that. Let's go for a quarter of the brightness. I have now made a collection of numbers that should help. These numbers, they all have the first 3 bits set. And then some other bits set. And I've just walked back through the bit patterns. You too can do this if you spend all your time reading hexadecimal. And I forgot what I looked at already. So I want 228 because that seems like a nice number. So we set the brightness to 228 and then we read RGB from what we actually pass to the script. And I'm not going to send, I'm just going to send red. And oh, look at that. So if I blank that off, the first pixel was red. And so it might be that we're driving the clock too long. I'm not sure. There was a lot of faffing at the start of this, and I don't want to chance the camera too much longer. And so I am happy to take any questions anyone has on Twitch or IRC for maybe 5 minutes, and then I'm going to drop off, and we'll figure out how to drive the rest of it in the future. And hopefully in between then I'll figure out what was wrong with this Raspberry Pi. And so I'll give it a couple of minutes. If you just want to ping me on IRC, if you're in an IRC I'm on, if you have a question, and if not, I'm going to go away. I'm not sure when I'm going to stream again. People really wanted to walk through my satellite testbed in the past, which is a very easy stream to do because I just need to SSH to the testbed. I do need to fix the Raspberry Pi, which is the head node. But I also need to re-cable the thing so it will fit in the cupboard properly, because this is the world we're in where I have to keep a testbed in the flat. And the testbed is just made of small single board computers, because all it does is fixed rate network delay. Oh, hi Matt. Matt, you can ask me any question you want right now. I just won't answer. I mean, I've been going for an hour and a half, which seems like quite a long stream. The oscilloscope I'm using, Warner, is it's a DSO-X. I don't know if that matters, and it's a 2014A. It might be like 6 years old now, so it was probably a newer model, but it's probably about the same. It is only 100 megahertz, and so it's not something you would actually probably have on your desk unless you're doing low frequency stuff. It got a little MSO enabled sticker that we had to put on when we enabled the MSO. But it is really cool. I'm a really big fan of these and how they work. I've used other manufacturers' stuff, and they're never as intuitive. Agilent definitely put in a lot of effort for how they set things up. And the things you can do with the serial decoder are really impressive. The digital channel, which I don't have the cable for, or I was actually planning to try and show that to someone, it makes very, very difficult to figure out where the 14 channels you have are actually connected and how you've routed them. Agilent make a education model of this oscilloscope now, and it's much smaller because it's been miniaturized in the last 5 years. I think they start at £500 in the UK. They have almost all the same features. All of the buttons are in different places, which means it's really difficult in the labs because we don't have a full lab's worth of either scope to go from one to the other, because the other ones, they have an extra row of buttons for a lot of the menu features, because buttons are obviously the expensive part. Yeah, I agree, Ed. The Rigol scopes are a lot cheaper. They are... The ones I've used have been difficult to use. So we had the really cheap, maybe £250 Rigol scopes, which are the lab scopes at the university I work at, and they're used for all teaching. They don't have features where you can do serial decode. and there's a lot of latency in how you look at signals. Here, a lot of things feel very, very crisp and immediate, and it just depends what you need, right? I mean, I'm not going to buy one of these oscilloscopes. I don't have £4,000 lying around to get one of these. But if I was buying it for someone to work with, even if they weren't working with it all the time, it would maybe be my choice. And obviously, this is a preference because I've used it and I enjoy working with them. The serial decoder is really helpful when you're working with things you don't actually know how they work. So I have a wireless router that I bought for £2 in some fire sale, and using one of these oscilloscopes and just being able to tune through the baud rate while I made it reboot a lot made me find the baud rate in like 5 minutes. And it was actually the second baud rate I tried. I don't know what the picoscope is. So I have in a box, I can't reach because it's under the table. I can't remember what it's called. So I've got one which is basically like a Raspberry Pi Shield, and it does like maybe 100 kilohertz, which would be okay for what we've done today. And it'd be fine for looking at LEDs, and it'd be great for looking at signal integrity for things which are okay. And so it wouldn't be a problem. I have, and I know George Neville Neal has one of these that he carries around. I backed the Kickstarter for the Pocket Pro, Pocket spelled P-O-K-I-T. That's just like it looks like a pen. It's an oscilloscope and multimeter. And it connects to your phone for a display. Okay, so like the picoscope. And it maybe does a megahertz. It doesn't go that high, but the form factor of it is great. And the Pocket Pro is rated for 600 volts, so it should be fine for doing real electrical work with, which I would never do. I mean, 5 is already too much. The software side of it's cool. I'm hoping actually the Pocket people will maybe open their software up so we can add. I mean, if you just give me the data, it's pretty easy to integrate it into SIGROC so we can actually do decode and stuff. I guess maybe I think so. There's a whole like LabVIEW package for the adjuvant scopes, and there's a whole like test bed infrastructure because these are designed to be integrated in a test setup. And so I think you can actually maybe dump the data from the scope over the network. And if you can do that, then you can build a logic analyzer from it. And I think they might be supported by SIGROC. It is hard to track down what's supported by SIGROC though. And I have a logic analyzer which I planned to go through the tutorial. And I have a really cheap oscilloscope which I soldered together actually. I don't know where these things are. I guess they're in the box labeled BSD can. That I could talk about in the future. I'm not sure. It was fun getting all the wires set up to talk about this. Okay. Any more direct questions, or I'm gonna drop off. I will look at the Twitch chat and everything. There's nothing in the Twitch chat. Okay. Thank you for joining. Thanks for saying thank you. I am going to stream again. I'm not sure. I might on Sunday. It depends how tired I am after a weekend of trying to not think about other stuff. But I will announce it on Twitter as I have in the past. I plan to dump the videos I've done so far and put them onto a YouTube, and I will tweet about that too. So there'll be lots of me going in the future, and you'll be able to watch it to your heart's content. So thanks for joining, and I will be noisy on social media, and I will do this again, and I will figure out how to get the whole Pi display going. Getting one LED going, I'm pretty happy with. It's more than I was expecting to have go. Okay, so thank you, and I'll speak at you again in the future.